Right. So let's start here, guys. What we're going to look at today is, I think, two things basically. My starting point whereby I'm preparing you to start doing particular functions like trigonometric functions, exponential, and so on. But first of all, I want you to understand what I call here function transformations. Maybe it's not the right way many people will call it, but I just decided to call it the function transformations. You'll see what we're talking about here. We're going to talk about things like scaling the variable, translating functions, horizontal shifts, vertical shifts, and all those things. All those things, you've got standard functions, then you play around with all these things like transforming variables, you have horizontal shift, you get some kind of variants of those functions which you are looking at. That's what we are looking at here. I hope it's clear what I'm trying to say. If it's not clear, then it's going to be clear as we go on. Now, let's start this way. Let's say we're given a function like, for example, y is equal to x squared. So the graph of this function, you all understand that it's a parabola. Roughly sketching it, it's a parabola which is centered, which has got a symmetry there. Altogether, we know that. So now, we want to play around this function in different ways. First of all, I would like to look at a variant of this parabola, whereby I've got a here, and then it's x squared. I think everybody here, if you look at this 2 here, in this one, we can say a is equals to 1. But then let's look at the situation where a is equals to, let's say 2, like 2x. And also we're going to be interested in looking at where a is equals to half, then x squared. What is important here, we need to see what is the effect of a on this kind of a graph altogether. So that's the kind of a transformation of function which I'm looking at. So now let's come to this one. Let's come to this kind of a graph. I hope it's clear to you. I'll take this thing here as this part here as our origin. And then you know that our x-axis now is going to be somewhere there, and the y-axis is going to be somewhere there. Altogether. Okay. So let's count in ones here. 1, 2. I'll just divide. I'll not write the numbers. Just say 1, 2, 3, 4. Maybe this side minus 1, minus 2, minus 3, minus 4. Altogether. And again this side 1, 2, 3, 4, 5, 6, 7, 8. So we're going to look at the standard graph as it is, like this. Y is equals to x squared. And since I'm talking to people who have seen this thing before, and we just want to focus on one thing, everybody knows that this is a graph which is actually cap up. Altogether. Okay. So now, we know the standard graph x squared as it is here. Let's see what's going to get here. If we go to 1, we say 1 squared is going to get 1. So we've got that point there on the line. Altogether. And if we go to 2 here, 2 squared is 4. So it's 1, 2, 3, 4. That point there will be on the graph. And then we've got 3 here. 3 squared will be 9. This is 4. 4, 5, 6, 7, 8, 9. So somewhere there. So but this graph is symmetric, we know. So which means this side at minus 3, 1, 2, 3. We're also going to get what? 9. At minus 2, we're also going to get what? 4. At 1, we're going to get again 1. Altogether. So let's try to sketch the graph. We sketch the graph roughly. Then the graph will sit here like this. Okay, that's the thing. That is for a is equal to 1. So now, let's move to another graph. In this case, let's take this one to be y is equals to 2x. What I'm doing this one, 2x squared. So now I'm multiplying the function by 2. So what we expect now is the following. Now, when we have 1 here, we will say x squared, which will give us 1. Multiplied by 2, that will give us 2, isn't it? So which means the graph will be somewhere there. If you look at what has happened, at 1, it was 1 before, now is 2. Which means it has grown faster than it was before, isn't it? It is higher than it was before. So when we get to 4, where is 4? Here, isn't it? It will be 8. So the graph will be somewhere there at 8. All together. So symmetrical again at 4 there is going to be there. Now the graph is going to look like this. At 0 is going to be 0 because 2 times 0 is 0, is it? Then it goes like that. Now what do we see there? The graph with an A which is greater than 1, the graph has risen fast upward altogether. It's actually narrowing altogether. So you must see that graph, that the effect of A there is actually making the graph grow faster when A is greater than 1. When it's 1, it follows the standard route. That is the standard graph altogether. Okay. So then let's check when it's half. Let's check when it's going to be half. Like A2 there is greater than 1 is representative of all the numbers greater than 1. So you must try to imagine what's going to happen when it's 3. When A is 3, when A is 4, and so on and so forth altogether. And when you get to A100, I think what we're going to at 1 here, the graph is very, very high, which means it's going to be very close to the y-axis altogether. That is, I think you must try to see that and feel it, that it's like that. Then let's take now y is equal to half x squared. Obviously at 1, instead of being 1, it's going to be half, because 1 squared is 1, half 1. So the graph is going to be there. At 2, instead of being 4, it's going to be 2. At 3, instead of being 9, it's going to be at 4, 5. Where is 4? 4 is here, is it? So 4, 5 is here. And then at 4 is going to be 16. Then it's going to be what? 8, which will be somewhere there. So similarly, at here, at this point, it's going to be there because it's symmetric. And there at 4, what is this? It's 4, no? It's 2, 3. It's going to be 4, 5. It's going to be there. So the graph now is going to come like this. It's lower than it was altogether. Okay, let's agree on something here. When I evaluate the function, let's say this point, and it goes up to that point there, I'll call that length the amplitude of the function altogether. So what has happened here? The amplitude of the function, when A was greater than 1, it increased. For every point, the amplitude increased altogether. And the amplitude, I'm just looking at that distance from the horizontal to the value of the function. That's what I'm saying, the amplitude altogether. Okay, so with the value, the amplitude there increases. So now what we see here, as A is increasing more than 1, the graph narrows up like that. But when A is less than 1, the graph opens up like that. That is very important to know when you're dealing with functions. Is that clear to everybody? Okay. Then let's check one thing now. Now there what we did, we just played with the amplitude. It's either 1 or greater than 1 or less than 1. Now, let's now play with the variable itself. The variable itself. What I'm trying to do here, I'm trying now to come up with a transformation like this. Y equals to x minus 1. Look at what I've done there. I've done an operation on x with x. It's just not multiplying x, but doing an operation with x itself. And then say all this now squared. All together. Now what happens now? This is what's going to happen. So this is the same function. It's still a parabola. It's still facing up, but there's a transformation which has happened there. Let's just check. this function, if you check it, it had a turning point here. When was that? It was when x was equals to 0. But what is really the function here? The function is a square. If I don't want to talk about same parabola, this function is a square. It says square x. All together? Okay. Here again it says square this. So then, since here, the function with the turning point when x was 0, when that argument x, which is being squared, was 0, I would try to sort of take that to this situation and say this one also is going to have a 0 when x minus 1 is equals to 0. What am I talking about? Here I'm talking about something which is squared, and there I'm talking about something which is squared, isn't it? But this one generates me an equation, which means now that this is going to imply that x is equals to 1. So now this turning point now is going to be at 1. All together. Now, if I now put 1 here for x, you will see that this will be 0 squared, isn't it? So the actual turning point here is going to be 1, 0. There, the turning point was 0, 0. So what do we do now? We will take that and come here at 1 there. Now what will happen really is that this graph now, instead of coming here, it will now change the position. What I'm going to do, I'm not going to plot the values, I'm just going to show you where the graph is going to, because the turning point is shifted to the right, is it? So I'm just going to sketch the graph. There is the graph now. It's going to be like this. 10 there. And then now be symmetric around the line x is equal to 1. All together. So what we do there? We call that a horizontal shift of the graph. So it's a transformation of the function. You understand what I'm saying? It has been horizontally shifted. So then, listen, from now I'm going to want you to take this sign here and read it as, not as minus. It looks like minus, yes, it's minus, but carrying a certain message. What's the message of this minus sign? It says shift to, in this case, shift to x equals to 1. Now that line is going to be shifted to x equal to 1. Isn't it? You know, the graph is going to, turning point is going to be shifted to when x is equal to 1. So, okay, when x is equal to 0, but when x is equal to 1. Are we together, guys? Okay. So shift to 1. Now, what will happen now if you are given a graph like this? What will happen if you are given a function like this? There is still a shift. Please, there is still a shift, isn't it? But what we see here is not the sign we say shift. We must then try to make us see the sign which says shift. But what do you need for that? We need to remember this. A minus sign and a minus sign, when they meet, they come together in one place. This one kicks this one here, and then it goes this way. And then this one jumps at the top there. Then it becomes what? A plus. So then if we want to do 2 minus sign back from plus, we have to do this. So how do we do it here? We're going to say this is equals to x minus, we put the brackets here so that this minus sign doesn't kick this one. Then square. All together. Then now we can read it this way. What is it going to say? It's going to say shift to x minus 1. So this new graph now is going to have a turning point at x equals to minus 1. So it's going to come this side. So the graph now is going to look like this. Do you see that? So now what has happened now? It's a transformation again. It's either that function is transformed, shifted to the right, or shifted to the left. Are we together, guys? Any questions that far? Now, this kind of situation is not because I want to discuss the parabola, no. I'm discussing the parabola because I'm familiar with it, and I want to remind you of that. But I want to take this experience to any other function when such kind of an operation is done on the variable, it's either the function is going to be shifted to the right or to the left. So take it to trigonometric functions, take it later to exponential functions, take it later to any other function you are going to meet. All together? All together? Please. Then let's look at another situation now. It's just a simple situation. Let's say here, instead of having x, we've got y equals to x squared plus 1. This graph is still going to have a turning point at x equals to 0. So we put the variable x equals to 0. But now we've got to now what will be the y coordinate. Then we take that 0 and put it here. Then you get that the coordinate y is equal to 1. Then that will be the turning point. So when we come to the graph here, this 0, 0 is no longer 0, 0, is 0, 1. Then that goes up somewhere there, which means this one is going to be a lift of the graph. Then we call it a horizontal, a vertical shift. All together. So then let's do this. I hope now you understand that. So now if we've got this situation now, this indicates a horizontal shift, isn't it? And when we've got that, then it's get a vertical shift. So now we see that this one will actually have a turning point 1, 1. So the graph goes horizontal, then goes up. Then in general, the equation of a parabola, this parabola, I think you've seen it before, it will look like a brackets x minus h, h for horizontal, plus k, k for vertical. Then when you look at it like that, we just tell that this function has got a turning point at h, comma, k. Then you can start plotting few points. Once you plot maybe 1 or 2 points of this, then you can just roughly sketch the graph. All together? Okay. Is that understood? Is that sitting square? Huh? Okay. So we saw that multiplying the variable, what does it do? It narrows the graph. All together. Manipulating the function itself, the variable itself, maybe subtracting or adding something, it shifts the graph this way. All together. Then adding a number outside the function here is a square. This is really outside the function. But you know what I'm trying to say, that the dominant function here is the squaring. And this is just an addition to that kind of action of squaring. Then we should see that one, that will lift the graph up or down. So we'll call that horizontal shift or vertical shift. H, we say horizontal shift. Like we said, they're going to read this thing as shift to H. And the K will stand for vertical. You see the sound of K. Vertical. Vertical shift. So you can see that somebody tries to put this equation this way was actually putting it in a suggestive way. If you read it properly and you've ever understood it, you will see that this is horizontal and this is vertical. It is put in a way that it suggests to you what is happening. That's what I mean by suggestive way. Are we together, guys? Good. Now, I think once we've understood these things properly like this, then now I think we are ready to start looking at special functions, knowing what happens when you play around with things like amplitude, knowing what happens when you play with things like what playing around with adding something to the independent variable and something like that. All together. Thank you. I think at that point I'm going to stop on that part of the work and say thank you for listening.